Imagine being born into pure chaos, moving at an absolutely incredible speed, and you've got just one single mission: survive a deadly, microscopic obstacle course and trigger another reaction. Oh, and if you fail, the entire system shuts down. Welcome to the Explainer. Today, we're tracking the high-stakes journey of a fast neutron trying to survive inside a nuclear reactor. We're going to look at the actual physics and the really elegant math behind how a tiny subatomic particle beats the odds.
So how exactly does a tiny neutron survive the deadly traps of a nuclear reactor? This is basically the ultimate question of reactor physics. When a fission event happens, neutrons are born fast, but to keep a chain reaction going, they've got to slow down to what we call thermal energies. The catch? The journey from fast to slow is absolutely packed with deadly traps just waiting to swallow our neutron whole. So how does it survive? And how do we actually calculate its odds of making it?
Okay, let's dive right into this. Here is our roadmap. First, we'll look at the neutron's thermal journey. Then we'll brave the uranium-238 danger zone, see how they escape the resonance traps, calculate the escape probability, and finally, wrap it all up with the resonance integral.
Part 1. The neutron's thermal journey. Born fast, but needing to slow down.
This whole calming down process has a formal name: thermalization. Basically, our fast neutron is bouncing around inside a moderating material. And with every single collision against an atom in that moderator, the neutron loses a good chunk of its kinetic energy. It's kind of like a billiard ball bouncing off the bumpers, slowing down a little bit more with each hit, until it finally reaches that crucial, slow, thermal energy state. But it is definitely not an empty table. There are some serious hazards on the board.
Which brings us to Part 2, the uranium-238 danger zone, navigating the intermediate energy region.
And this brilliantly illustrates exactly what that danger zone looks like. Over on the far right, we've got our fast fission neutrons, and way over on the far left, the safe haven of thermal energy. But do you notice those sharp, jagged dips right in the middle, marked by the dotted lines? Those are capture resonances. As the neutron loses energy in the moderator, taking those curved, step-like paths downward in energy, it risks falling straight into one of those U-238 traps.
Let's break down the key takeaways here. The neutron starts fast on the right, needs to get to the left. Simple enough, right? Well, that middle zone is literally a minefield. In this specific energy band, the probability of uranium-238 absorbing the neutron just spikes dramatically. Every single collision with U-238 carries the lethal risk of the neutron being completely lost to resonance absorption. And obviously, if too many neutrons are absorbed here, the chain reaction just completely dies out.
Part 3. Escaping the resonance traps. The physics leap.
It really all comes down to scale. These U-238 capture resonances are incredibly narrow. We're talking only about 2 electron volts, or eV, wide, and they're spaced out by roughly 20 eV. But here's the trick. When a neutron actually collides with the moderator, the chunk of energy it loses per collision is much, much larger than that tiny 2 eV width.
Because that energy loss per collision is so huge, most neutrons literally jump right over the resonance traps. Think of it like taking a giant 50-foot leap over a tiny 2-foot puddle. Now sure, if a scattered neutron happens to emerge with an energy that drops it perfectly inside that tiny 2 eV window, yep, it gets captured and absorbed. But statistically, because the jump is so vast and the trap is so incredibly narrow, most neutrons just leap cleanly right across the danger zone. They land safely in the gaps where capture cross-sections are super low, and they just keep on scattering until they reach that thermal safety.
Part 4. Calculating escape probability. Moving from physics straight into the mathematics.
Okay, so to calculate our actual odds, we need to build an equation. Our ultimate goal here is finding P, the resonance escape probability. This is simply the ratio of neutrons that survive to reach lower energies, which we call Q of E, divided by the initial number of fast neutrons, Q0. To figure all that out, we have to look at the total cross-section, sigma T, which is really just the combined probability of either absorption or scattering happening.
Let's see how this all builds into our core calculation. Step 1. We define the loss of our slowing down neutrons as the actual rate of absorption in that specific resonance region. Then, Step 2. We rewrite our neutron flux in terms of our slowing down density and total cross-section. And finally, Step 3. By combining those and integrating the resulting equation right between the start and the end of the danger zone, we can calculate the exact number of survivors.
Part 5, the resonance integral, the final equation.
Now, here is where we really tame the mathematical complexity. We already know the total cross-section is absorption plus scattering, right? But if we assume that scattering is much, much larger than absorption and that it's relatively constant, the math just beautifully simplifies. By plugging in the atom density of the fuel, our survival probability, P, actually becomes a super clean exponential function.
And that simplification introduces a really vital new concept, the resonance integral, which is represented by the letter I. As defined in equation 3.12, it's the integral of the absorption cross-section over energy divided by energy, all across our defined limits. Conceptually, the resonance integral takes this entire wildly complex, jagged U-238 danger zone and neatly packages it up into one single mathematical value. Engineers can then just plug that right into their reactor models. It's pretty amazing.
So the crucial point is exactly how this all fits into the big picture, and it's perfectly summarized by this quote from our source. With the resonance escape probability taken into account, the net number of neutrons produced in the thermal energy range becomes eta times epsilon times P. Our hard-fought survival metric P, the resonance escape probability, slots perfectly into the core formula that determines if a reactor can actually sustain power. Without P, we have no idea how many neutrons survive, which means we can't sustain a chain reaction.
It's truly mind-bending when you take a step back and really look at it. A tiny subatomic particle is bouncing around, and its ability to literally leap over a microscopic 2 eV wide gap in an energy spectrum is the difference between a highly successful nuclear reactor and a completely dead pile of metal. It really makes you wonder, if just a 2 eV gap determines the fate of an entire reactor, what other atomic-scale miracles are powering our cities right now? Think about that as you review these equations, and keep exploring the incredible world of reactor physics. Thanks for joining me on this explainer.